Good afternoon, everyone. I'm Davide, a second-year PhD student in Trento. And first of all, I want to thank the organizers for having me. This work was done in collaboration with my supervisor, Sanni Vagnozzi, and Luis Escamilla. And okay, I'm going to be very brief on the Hubble tension because it has been discussed in great details throughout this conference here. Basically, the Hubble tension is just the mismatch in the inference of H0, the current expansion rate of the universe, as inferred by, on the one hand, via direct measurement, and on the other hand, by cosmological model-dependent measurements. Up to date, the two most precise results are the 2018 Planck results, giving roughly 68 kilometers per second per megaparsec, and on the other hand, the 2024 SHOES result, giving roughly 73 kilometers per second per megaparsec. Okay, in the context of the Hubble tension, Baryon Acoustic Oscillations play a very important role, as they contribute to establish a no-go theorem which precludes post-recombination solutions to the Hubble tension. And why is that the case? Baryon acoustic oscillations are basically measurements of angles, and as shown by this chain of equation here, they are sensitive to the product of RD and H0, where RD is the size of the sound horizon at baryon drag. So the point is that if we trust baryon acoustic oscillation measurements, and if we want to raise H0 as to solve the tension, we are forced to lower the value of the sound horizon, and this calls for pre-recombination new physics, as the sound horizon is sensitive to what happens before recombination. At the same time, we can also calibrate the sound horizon in a way that is completely independent from CMB measurements by using the Big Bang nucleosynthesis inference on the abundance of baryons and an information of omega m coming from baryon acoustic oscillation and possibly supernovae to build the so-called inverse distance ladder, which gives a result for H0 of roughly 68 kilometers per second per megaparsec, which is consistent with Planck, but in tension with SHOES. Finally, baryon acoustic oscillations and supernovae constrain very tightly the expansion rate of the universe, the E of Z, in the low redshift regime, preventing large deviations from λCDM. All these things together combine in a no-go theorem, which, as I said before, precludes post-recombination solution to the tension. And as we saw, this no-go theorem hinges in a crucial manner on BAO measurements. Of course, some objections to the no-go theorem were raised, in particular about the possibility of loopholes that are due to the assumption of a fiducial cosmology in the BAO pipeline. Indeed, the BAO pipeline needs the assumption of a fiducial cosmology, which is typically λCDM, and the fiducial cosmology is needed at various steps in the pipeline for transforming redshift and angles into comoving coordinates, for constructing a template to be fitted to fit the baryon acoustic oscillation feature out of the tracer power spectrum, and finally to perform the reconstruction, which is needed to basically lower the error bars. So the question is, what happens if we assume a fiducial cosmology which is vastly different from λCDM? Would the recovered alphas or the BAO feature be very different from the one that we get? In this work, we didn't explicitly answer this question, but instead we decided to play devil's advocate, and in particular, we assumed that the adoption of λCDM as a fiducial cosmology results in a misdetermination of the alphas, or in other words, of the BAO feature, and in particular, that the inferred acoustic angular scale is biased low. Let me try to clarify the picture with this diagram here, which represents a very schematic and far from reality BAO measurement, a person here is pointing her telescope to the standard ruler, and we assume that the standard ruler was calibrated. But due to this devil here, which represents the assumption of lambda CDM, she measures an angle, theta d, which is smaller than the actual one, than the real one, which is this theta d star. What's the point here? The point is that if we look at an object through a small angle, we think that the object is very far away from us. And since the distances are inversely proportional to h0, the value of h0 that we infer is lower than the real one. On the other hand, if we were to measure the real ones, the real angles, which are in our hypothesis bigger than the one that we measure, we would infer an h0 that is larger than the 68, say, kilometers per second per megaparsec that we get combining Baryon acoustic oscillation with inferences of or the abundance of baryons from BBN. And so what we did was to just rescale with a redshift independent factor epsilon our angles, our Baryon acoustic oscillations, to get newer angles, theta d star, and you can think of this epsilon here as the ratio between the angles that we measure, because we assume lambda CDM, this theta d, and the angles that we would need to measure to get an h0 of roughly 73 kilometers per second per megaparsec. So the value of epsilon is hand-wavingly justified by this chain of equation. If we assume a value of the sound horizon of roughly 147 megaparsec, we get an inference of h0 of roughly 68 using Baryon acoustic oscillations. So this term epsilon here cancels somehow the h0, the old h0, and kind of imposes a new value of roughly 73 h0, which is the value needed to solve the tension. So we asked ourselves, is this modification to the BAO enough to rescue late-time solution to the Hubble tension that were excluded by the no-go theorem? And to do that, we consider the following dataset and priors. So first of all, we consider SDSS, excluding Lyman alpha. And the reason for that is that we wanted a conservative BAO dataset to make our life harder, in a sense. And that's also the reason why we didn't consider DAISY, because we didn't want to mix the Hubble tension with possible hints of deviations from lambda CDM that are present maybe in DAISY. Then we have the rescaled BAO, which are basically our SDSS BAO rescaled by the factor epsilon that I showed you before. Then we have the Pantheon plus, then a compressed version of the Planck likelihood, featuring the sound horizon and an estimate of the abundance of baryon that is anyway compatible with the one obtained from Big Bang nucleosynthesis. And finally, a prior on omega m, which is very broad, as you can see from the sigma, that is there just to keep our results consistent with the many inferences of this cosmological parameter coming from, I don't know, cosmic chronometers, lensing, and so on and so forth. So again, the idea was to test popular late-time modification to lambda CDM that were proposed as solution to the Hubble tension, and see if this modification of Baryon acoustic oscillation is enough to rescue them as solution to the Hubble tension. So let us start with the simple example, which is lambda CDM, and let me guide you through this plot here. So here we have the combination of dataset that I presented you earlier, and as you can see, all of them feature the Planck likelihood and the prior on omega m. Okay, we can start from, for example, SDSS. Here is the blue contour, and then we can move to SDSS-R, which are the rescaled BAO. And as expected, we see a pronounced shift towards higher values of H. But this shift is anyway cancelled when we introduce also Pantheon plus in our dataset. You can see like is the dark blue or black contour here. So the point here is that even if we rescale the BAO, the constraining power of the strong constraining power of Pantheon plus of supernovae cancel the positive shift towards higher values of H. So the results look kind of good, in agreement with what we were expecting, but we weren't completely satisfied because according to this simple argument here, we expected a value of H naught roughly around 73 kilometers per second per megaparsec, and we also expected a kind of rigid shift in H naught, meaning that all the other cosmological parameters are untouched. The other cosmological parameters enter here. But what we actually see from this plot here is a shift in H, in the green contour, but not up to 70.73. And we also observe a shift in omega m. So we are not able, only considering rescaled BAO, let alone the case with Pantheon plus, to get this rigid shift. And we wanted to understand why. So we looked at the best fit curves to the data. So we have, with diamonds, we have SDSS points. With circles, we have their scaled version. And we also plotted the residuals. And in the residuals, we added also crosses that takes into account the difference between data, in this case SDSS-R, the rescaled one, and the model is the okay, no? Oh, anyway, and the model is the rigid shift in H naught. And the point here is that by playing a sort of chi by I, we are not able to discard a rigid shift in H naught. So this does not explain why our posteriors does not show a rigid shift in H naught. And the reason for that, the reason why we couldn't achieve this rigid shift in H naught is exactly this CMB point here at the redshift recombination, which precludes the rigid shift. The rigid shift is this green line here, and as you can see, this is like discarded by this point here at recombination. And this is also the reason why we have this correlation here between H and omega m. And due to this point here, due to the geometric CMB point, we cannot have a rigid shift, otherwise we would introduce a tension between CMB data and BAO data. So in the case of lambda CDM, we couldn't achieve a shift in H because of two reasons. Because of Pantheon plus, because when we consider Pantheon plus, the situation is restored back to the original ones, and also because of the CMB point, geometric point. Okay, let me move to more complicated models as the WCDM model. Here we got a result that was pretty interesting. Indeed, the shift, look again at the green contour here, the shift in H was in the opposite direction as expected. Indeed, we get a quintessence-like dark energy with H that was lower than expected. And so again, to try to understand why, we gave a look at the fit to the point. But before moving on, I wanna stress again the fact that including supernovae, the situation is restored back to the original one, and this again is due to the strong constraining power of supernovae preventing deviations from lambda CDM. Okay, so basically this fit here, this plot here, justifies the preference for a quintessence-like dark energy. We can play a sort of chi by I, looking at these residuals here. The crosses this time represents a phantom dark energy, which is the kind of dark energy that we expected. A phantom-like dark energy like this, and we set a value of H naught roughly around 73. This combination of parameters here is allowed by the geometrical degeneracy of CMB. And we can see by playing a chi by I that crosses lose the race against circles, and that's the reason why we got this quintessence, this preference for quintessence dark energy. Actually, this model here, which is more complex than lambda CDM because it adds an additional parameter, showed us also that our picture here, the devil's advocate picture was a bit naive. Because we thought that because we thought in terms of, okay, an object looks distant, so the inference of H0 should be lower and so on and so forth. But actually, complex models such as WCDM, which has a parameter, can vary their parameters in a way to justify objects that are closer to us without increasing the value of H0. So this makes the picture more complicated than we expected. And finally, I want to show perhaps the most interesting result, which is the one for lambda S CDM, which is a model that features a transition in the cosmological constant from negative values to positive values, roughly around z equal 2. And this is very interesting because, of course, the green contours, the rescaled BAO displays a shift in age, but this shift is not completely cancelled by considering also Pantheon Plus. You can see here that we still are around 70, and the reason for that, okay, and this is consistent, okay, with the theoretical prediction. If you have a transition roughly around 2, you get a value of H0 roughly around 70, and the reason for that is that if the transition happens before 2 or roughly around redshift 2, the E of Z, the unnormalized expansion history, is still able to fit the supernovae, the shape of the supernovae. And that's the reason why this model is still able to get to feature an age up to 70. Okay? Okay, so to the conclusion, we asked ourselves whether a bias in the BAO measurement would be sufficient to rescue a number of popular post-recombination proposals on the market, and the answer is no, basically because of two reasons. Because of the strong constraining power of Pantheon Plus, preventing, and supernovae in general, preventing large deviations from lambda CDM, and also because, as I showed you in the lambda CDM case, but it was roughly the same for all the other models, a rigid shift like the one that we expected would introduce a tension between the BAO and the CMB data. And yeah, that's it. Thank you. Oops.
Thank you for the nice talk. Any questions?
All right, thank you for a very nice talk. It was very interesting. So actually, I was wondering because in DESI for the DR2 analysis, we kind of like reanalyzed the entire thing, assuming W0 WA cosmology, and the results were pretty much the same, like the alphas were pretty much the same as when assuming lambda CDM. So I was wondering if like you could think of another reason why the alphas could be biased low, and that could like, you know what I mean?
Yeah, the point of this work was kind of a proof of principle, right? We wanted to see if changing, if a dramatic change in the angles would result would save basically post-recombination solution to the Hubble tension. And the point is that I'm aware that there are analyses that have tried to use different fiducial cosmology to redo the BAO pipeline. But the point is that what happens if the fiducial cosmology is very far from lambda CDM? For example, a W CDM with a value of W, say, minus 1.2 or minus 1.3, what happens in that cases?
Okay, like, yeah, I agree. Like a very extreme case, right? All right. Nice, thanks.
Any other questions? No? So let's thank Davide again.